couple of examples. First, an antiderivative problem. If we're given a marginal cost function, so let's say I know what the marginal costs for my product are, and I happen to know what the fixed cost of producing my product is, how do I take that information and reconstruct the total cost? Remembering that the relationship between total cost and marginal cost is a derivative relationship. Right? The derivative of C is what gives me C prime. So if I want to find the total cost from the marginal cost, what I need is an antiderivative. So then my question to you is, how do I take the antiderivative of 5x squared minus 5x? Let's start with the 5x squared part. So increase the exponent by 1, so x squared becomes x to the third, and then divide by the new exponent. So increase the exponent by 1, it becomes 3, then divide by that 3. That gives me the antiderivative for the x squared. And because derivatives have the linearity theorem, so do antiderivatives. So this 5 will just come along for the ride, and we'll get 5 times x to the third over 3. What does that mean about 5x? What's its antiderivative going to be? What's the secret exponent here? In front of that x, there's a little 1 that we don't always write. So if I'm taking the antiderivative of x to the power 1, what am I going to do? Increase this exponent by 1, becomes x to the power 2, and then divide by that new exponent. So if I clean up this formula here a little bit, what I'll get for my antiderivative so far is 5x to the third over 3 minus 5x squared over 2. But what am I forgetting? What haven't I written in my antiderivative yet? Yeah, I haven't written in my constant, my additive arbitrary constant, my plus c, and I need that because this is what's going to allow me to match the antiderivative to the fixed cost information that we have in the problem. We know that c of 0 has to equal 8,000. And if I don't put this plus c there, c of 0 is going to be 5 times 0 over 3 minus 5. c of 0 is going to be 0, unless I have a constant sitting out in the front here that I can use to match up my fixed cost. So now I'll use that information, the fixed cost information, to solve for my additive constant. C of 0 is equal to 5 times 0 squared over 3 plus 5 times, cubed over 3, 5 times 0 squared over 2 plus c. But that's equal to 0, that's equal to 0. So c of 0 is just equal to c. But I need that c to equal 8,000. And so then that tells me that I should just choose the single antiderivative that has for its arbitrary constant 8,000. So if this was my marginal cost function, then this is going to be my total cost function. Found its antiderivative by taking each power of x, increasing the power by 1 and dividing by the new power, and then adding the arbitrary constant at the end that we can use this data point to solve for. Let's do a problem then that has us computing a definite integral, which is what we ultimately want this technique for the sake of the project. Let's use the fundamental theorem of calculus to evaluate this definite integral. So the function is 4x squared plus 4, all divided by x squared, taking the antiderivative from x equals 4 to x equals 5. So what it is that we're computing, I've got the graph of the function 4x squared plus 4 all divided by x squared. That's this graph shown here in red. And what we're trying to compute here is the area underneath this graph between x equals 4 and x equals 5. So it should be the area, whoops, this needs to say 4 here. It should be the area of this little blue thing. Can't quite get that to match. So this blue area is what we want. If I'm looking on my graph paper, I can just count my graph paper squares to at least get an estimate. Right? Each of these squares is, let's see, it's a half a unit on this side, and it's 1 unit. So each of these is 1/2. So I've got 1, 2, 3, 4, 5, 6, 7, 8 of them. So that's a total area of 4. And then I also have a little teeny tiny sliver up here that I can't quite count as a full square. So I've got 4 plus a little bit is what we expect this area to be. Let's use the fundamental theorem of calculus to get an exact answer. So what we need, according to the fundamental theorem of calculus, is we need an antiderivative for my function. I need to evaluate, or as we sometimes say, plug in, my limits, x equals 5 and x equals 4, and then I need to subtract. That's what the fundamental theorem of calculus tells us about how to apply a definite integral. And the hardest step, I think, is actually finding the antiderivative for this. Now, this is a fairly complex-looking integrand function that we're trying to take the integral of. So before we do any calculus to it, let's try and simplify it with algebra. ABC, algebra before calculus. Before you do any calculus, simplify using algebra as much as possible. I'm going to do that by splitting up the addition in the numerator of this rational expression across the division. And what that means is I'm just going to rewrite 4x squared plus 4 over x squared by undoing an addition across a common denominator. So it looks like this, right? And what that allows me to do is it allows me to simplify this first term. 4x squared over x squared is just going to be 4. And 4 over x squared, before I do any calculus with that, I'm going to rewrite it as a power of x, namely the minus second power of x. So that now the thing I'm taking the derivative of looks a lot simpler. Now it just looks like a sum of 2 powers of x. And so now we know what to do with that when it comes to antiderivatives. So my antiderivative is going to be, first of all, what's an antiderivative for the function 4? How many powers of x are there in front of 4 secretly, right here? Well, there's none, so we could call it x to the power 0. And writing that in then gives me the clue to how to take the antiderivative of x to the power 0. What are my 2 steps? To find an antiderivative for a power. Increase the exponent by 1. And then divide by that new exponent. So an antiderivative for x to the power 0 is x to the power 1 over 1. But both that exponent of 1 and that division by 1 are transparent. We could just erase them. But what we find out when we take this antiderivative is that the antiderivative of 4 is 4x. You can always check your answers, by the way. If you're unsure whether your antiderivative is right, just try taking the derivative and you should end up back where you started. Right? So you can always check any inverse process that you learn in mathematics. You can check your answer. So that's for the first term. Now what's going to happen with 4x to the minus 2? What will an antiderivative for x to the minus 2 be? Increase the exponent by 1. Perfect place to make a sign error. Negative 2 plus 1, negative 1. And then divide by that new exponent. And my 4 is going to come along for the ride. And I can do a little bit of simplifying here. 4 divided by negative 1, that's going to give me a negative 4. So there's an antiderivative for me. I could also simplify and turn this negative 1 power of x into an x in the denominator. Probably a good idea just to make this look a little nicer because we're going to have to do something with this next. So there's an antiderivative for the function that we started with, 4x minus 4 over x. And I suppose, if I'm being consistent, we'd want to add a plus c here, right? An arbitrary additive constant. But the thing about adding a plus c here is even if we did, the next thing that we're going to do, plugging in numbers and subtracting, because c is a constant, it's going to appear in both the number that I get here and the number that I get there. And when I do the subtraction, my plus c is going to go away. So the good news is we don't need a plus c when we're doing a definite integral. I'm just going to kind of temporarily put it in there. So we've got our antiderivative. Now let's use it. To actually use it, we'll have to plug in these 2 values, which are the limits of my integral, x equals 5 and x equals 4. So capital F applied to 5 is, what is that going to be? 4 times 5 minus 4 over 5. That's 20 minus 0.8. That's 19.2. F of 4. 4 times 4 minus 4 over 4. That's 16 minus 1. That's 15. Now I've plugged in my two values according to the fundamental theorem of calculus. Then what I have to do to finish, to find the definite integral, is subtract. 19.2 minus 15 is going to give me the value of this integral. So integral from 4 to 5 of 4x squared plus 4 over x squared with respect to x is equal to 19.2 minus 15, otherwise known as 4.2. So if you remember those little slivers of area that we couldn't quite count that were a little bit more than the 4 than we were able to count on the graph paper, well, it turns out 4.2 is the value of that area.